Hi guys, welcome back to Think Tank Online Learning. Okay, so in this video we're going to talk about area of surfaces in space. Okay, so we're given a problem. Find the area of the region cut from the plane 3x plus 2y plus z equals to 6 by the cylinder of the walls x equals to y squared and x equals to 2 minus y squared. Okay, so this is our x limit. Okay, so the first thing you have to do when you want to find the area, we're going to use the double integrals. Okay, so our double integral, since we're dealing with vector, so this is vector calculus. Okay, so the formula finding area of the surface is equals to double integral of the region, okay, the gradient of the vector function, magnitude of the vector function over vector function times, okay, let me just say p dA. Okay, so in other ways this is equal to ds. So let me write here gradient of a function, magnitude of the gradient of a function over gradient of a function times p is equal to ds. Okay, then p is equal to vector k. Okay, equal to vector k. In other ways, p is equal to 0 0 k. Okay, so now I want to find the area. So what are we going to do? So there are many ways of finding ds, but I think the easiest way is to make z sub with the formula. Then after making z sub with the formula, you say ds is equals to the partial derivative of x squared plus partial derivative of y squared plus 1. Okay, so this is equal to ds. Okay, so this is the formula I'm going to use, and from this problem you know that z is equal to 6 minus 2y minus 3x. We just made z sub with the formula. Okay, so and I want to find the partial derivative or the partial derivatives of this function. So I'm going to say fx, that means I am going to differentiate this function with respect to x, and I'm going to treat all other variables as constants. So this is equal to negative 3x. Okay, so the derivative of 3x is just negative 3. Okay, then the partial derivative of this, we're going to differentiate it with respect to y, is going to be negative 2. Okay, so we're good here. That means the area is equal to double integral of the region, and the region is bounded by the walls of this cylinder x equals y squared and x equals 2 minus y squared ds, which is equal to the root of f squared x plus fy squared plus 1 dA. Okay, so now let us say double integral of r, and you know that f squared is negative 3 squared plus negative 2 squared plus 1 or under the square root of dA. Okay, good here. Double integral r, and 3 squared, that is 9, 2 squared plus 4, it's now 13 plus 1, and it is root 14 dA. So now I want to evaluate the limits. So the region is bound by the limit of this was. Okay, but now since I'm now in the xy plane, let me graph them here. So this is y and this is x. Okay, and I think integrating is easy. What is only hard to evaluate the limits. Okay, so now we have this equation: x equals 2, y squared. So if we make y subject of the formula, we're going to say y equals root x, and the graph of y equals root x looks like this. Okay, this is y squared is equals to x. This is same as y equals root x. Then now want to plot the graph of x equals negative 2y squared. We're going to just apply the transformation here. So I'm going to move 2 steps. So this is 0, 1, 2 here. Okay, and I'm going to reflect it along the y-axis. Okay, and this is going to be the graph of x equals to 2 minus y squared. Okay, and so that means this is the region we are concerned about. Okay, but we have to find what is the value of y here, what is the value of y here. We're already given the limits of x, but we're not given the limits of y. So if we solve this equation simultaneously, let me write the equation here. X equals to y squared, that is the first equation. X equals to 2 minus y squared, that is the second equation. Okay, now I'm going to solve them simultaneously. Okay, so y squared, I'm going to equate equation 1 to equation 2. Y squared equals 2 minus y squared. That means 2y squared is equals to 2. Dividing both sides by 2, I'm going to say y squared equals to 1. And taking the square root on both sides, y squared was plus or minus 1. So, limits here, this is equal to 1. And this is equal to negative 1. And now I want to find the perfect order of integration. So, now if I say dx dy, I'm going to integrate with respect to x first, and I think it's very wise to do that than saying dy dx. Okay, because if I say dy dx, I now have to change the limits. Okay, because now from this information, I know I'm going from here, which is y squared equals to x, that is the lower bound of x, and x minus x equals to 2 minus y squared, that is the upper bound. But if I want to change this sort of integration, it is going to be very difficult for me, so I'm going to leave it like that. So now I come here, as the area of the surface is equals to, I'm going to integrate respect to x, so y is going to be my outer integral, so negative 1 here, sorry, positive 1 and negative 1. Then what is the upper bound? The upper bound equals to 2 minus y squared, and the lower bound y is equals to y squared. Then what about ds? Root 14. Then dA is now dx dy. Okay, so if you are confused about which one is the upper bound and which one is lower bound, okay, so say this coordinate is 2. Okay, so now I want to find, you can just choose a number between 0 and 2 and just plug in. So if I say when y equals to 0, so when y equals to 0, I know that from the first equation, x is equals to 0. What about here? When y equals to 0, x is equals to 2. So that means this one is the upper bound and this one is the lower bound. Okay, and I'm going to repeat. You choose the number that is between the range from 0 to 2. Okay, and now let us perform our integrals. Okay, so the first thing, this is just a constant. We're going to integrate with respect to x, so that means 1 negative 1 root 14 x, our limits 2 minus y squared dy. Okay, and now I'm going to say upper bound minus lower bound, negative 1. So this is going to be root 14 2 minus y squared minus root 14 y squared dy. Okay, and we're good. So let me just expand. I want to make things easier. So this is going to be root 14 2 root 14 minus root 14 y squared minus root 14 y squared dy. Okay, so this is equal to 1 negative 1. So we got 2 root 14 minus 2 minus y squared minus root 14 y squared minus root 14 y squared, same as 2 root 14 y squared dy. And if we have a situation like this, you know that this limits ranges from -1 to 1 or -2 to 2. Okay, the best way you can do that, let's say you have a line here. Okay, so this point we're going to call it 0, we're going to call this point 1, and -1 this is equal to 1. So we know that this distance is the same as this distance. So if I want to find the distance from here to here, I can just say this distance times 2. Okay, and if your lower bound is 0, 0 is easy to evaluate than -1. 0 is easy to work with. So now what I'm going to do, okay, I am going to say 1 0, but I'm going to multiply that distance by 2, because I'm going to multiply the magnitude 2, then 2 root 14 minus 2 root 14 y squared dy. Okay, and now I'm going to integrate this x to y, so I'm going to add, just increasing the power, then divide by the new power. And if I do that, I'm going to say 2 another bracket 2 root 14 y. The other way you can just factorize, you can just pull root 14 out here, so it's going to be 2 root 14 y minus 2 root 14 y to the power 3. Okay, then my limits 1 and 0. Okay, and now I'm going to say upper bound minus lower bound, so it's 2. So if I replace y with 1, then minus 0, so I'm going to say 2 root 14 minus 2 root 14, sorry, this is was equal to y to the power 3 over the new power, which is 3. Okay, minus the lower bound. If I put 0 here, I'm going to get 0. Okay, over 3. Okay, and if you punch this in a calculator, you're going to obtain 8 root 14 over 3, and that is the area. Okay, so we could have used this method, okay, just the same, the vector gradient. Going to just say the vector gradient, we're going to just differentiate here. It's going to be 3 2 1. Then after that, we're going to find the magnitude, just the square, x squared plus y squared plus z squared. Then after that, we're going to say the vector gradient times p, which is the value of k, the vector k. And after that, we're going to obtain the same value, root 14. Okay, thank you for watching. Don't forget to subscribe to my channel.